This vodcast is going to be on Hess's law. It is one of a property of thermodynamics. So just as a reminder, enthalpy is a state function. So it doesn't matter the path in which we get to something. All we care is about where we start and where we end. So just like an example, going from here to school, there's several different ways we can get there. All that matters is where you start out and where you end. So that being said, Hess's law is in going from a particular set of reactants to a particular set of products. The change in enthalpy is the same whether the reaction takes place in one step or a series of steps. So let's kind of illustrate this by example. So let's say we have a reaction. Whoops. So we have N2 plus O2 produces 2NO2. And we want to know is what this delta H of this reaction is. Well, it'd be a good idea to figure out what delta H of the reaction is just before we actually do it, to give us a sense if it's going to absorb heat or give off heat. Well, we have two different equations here, two similar, of reactions that we have done, and we know what the delta H is for each step. And since each of them both have the same species, except for there is no NO in the top one, it's only here. In Hess's law, we basically can add these two up, and it can produce what we want in the beginning. So if you notice here, if I add these two reactions up, these two steps here that I have, I'll have an N2 because this is on the reactant side. I'm going to add up these two O2s here, so that's going to be a 2O2. So I added these two up to get that. Okay, I have a 2NO in the product side on the first step and a 2NO in the reactant side in the second step. If I add those up, they're actually going to cancel each other out. So they will not be in the final answer. So I'm not even going to put it down. And then I'm going to carry down the 2NO2 down. And if you notice, when I added these two steps together, it looks exactly like the one that's up here. Well, since I can add these two together, I can also add their delta H's from each step. And if you plug this in your calculator, so I'll plug this in, 180 minus 112, we're going to get, let me plug this in 1 second. We're going to get 68 kilojoules after all said and done. So 68. So by Hess's law, I was able to determine that this reaction is actually endothermic and it absorbs 68 kilojoules of heat without actually having to do the reaction. So if I need to do the reaction, I can get an idea as to what the outcome will be before I even do it. And this was possible because I knew the delta H's of two similar reactions that I was able to manipulate to get to the reaction I wanted. So this follows a state function. You can have 1 step to 10 steps. As long as it looks like this, I can find out what my delta H is. There's a couple two general rules that you should follow with Hess's law. If a reaction is reversed, the sign of the delta H is also reversed. So you basically flip a reaction and then the sign will change. And delta H is directly proportional to the quantities of reactants and products in a reaction. What that means is that here I have water, liquid water going to gaseous water. I know that it absorbs this amount of heat. If you notice, if I double the coefficients times 2 from the first one here, I also double my delta H. So any coefficients you plug here will affect the delta H of that reaction. Alright, so let's do an example that kind of illustrates this. So here's a similar example. I have PbCl2 solid plus chlorine gas, and it's going to produce PbCl4 liquid, and I want to know what delta H is. And here I have two steps that can help me out to figure out what that delta H will be. One of the first ways I tackle this is I check to make sure my reactants are on the correct side and my products on the correct side. And if you notice here, this PbCl2 solid is a product on this step, but it's a reactant on this step. So according to Hess's law, I'm going to flip this reaction around, and that's going to change my sign of my delta H. For the sake of time, I'm going to do that. So I colored this blue just so you can see that I flipped it. and my sign on my delta H has now changed to a positive number. So just so you can get an idea, it saves my space on my board, I've done that. So now I can take a look. All my species are all on the correct sides, and if I add these two together, I should get the product that I'm looking for. So I'm going to add these two reactions up. I have only one PbCl2 from both sides, so that's going to carry down. I notice here I have a Pb on the left side and I have a Pb on the right side. They're actually going to cancel each other out. Here I have two chlorines on the left side, but one chlorine on the right, so I'm only going to carry down one chlorine. And then I'm going to form PbCl4. That's going to carry down on the product side. So, and this example is pretty easy. It's just a matter of flipping and seeing what cancels out and how do you add these together. Now that they look exactly like what it does up here, I'm just going to add up my delta H's now. So I plugged this in my calculator and I got 30.2 kilojoules, and it's positive. So here's an example where we were flipping an equation to change the sign, and it was a very simple one where we just added the two together again, and we got 30.2 kilojoules. Okay, this one's going to be a little bit more complex with this one. So as you see here, we have the reactions up here. So I want to know what delta H is for this reaction. So 2 carbon plus oxygen plus water produces 2 H2CO2 liquid form. And now I have 3 reactions here that I can use to manipulate to see what my delta H for this reaction would be. Okay, one of the first things I want to first figure out is, do I need to flip any of my reactions to make sure my reactants and products are on the correct side? So my carbon is a reactant. I have it here, so that's good. I have an oxygen as a reactant. It's a reactant here, so that's good. I have water as a liquid up here, but as I look at my reactions, I see that water is a liquid in the product side of this reaction. So that's not good. One of the first things you should always do is to check. So that means I'm going to have to flip this reaction over to make sure that my liquid here is a reactant is the same as on top from what I'm looking for. So to save some time, I'm going to flip it, and I change it to a different color just so you can see visually that I flipped the reaction. And remember, whenever you flip a reaction, you have to change the sign on the delta H. Okay, now that I flipped it, I gotta make sure that my elements all balance out. So I can see here that I have a 2 in front of this carbon, so that means I'm gonna have to multiply this reaction all times 2. So this is gonna be gone. I'm gonna put a 2 here, and then I gotta multiply 110.5 times 2 to get my new delta H. Okay, so using my calculator, whoops, no, camera's not working. So using my calculator, I get a negative 221 is my new delta H for this reaction because I multiply it times 2. I notice that I have no CO up here on top, and I have a CO here, so that means I gotta multiply this bottom one times 2 to make sure that my COs cancel out. And when I do that, I gotta multiply my 33.7 times 2, and that's gonna be 67.4 is the new number here. So 67.4. Okay, well, I also noticed that there's gonna be no H2CO2 gas will be gone in my overall, so that means I gotta multiply this whole thing times 2. 2 seems to be a reoccurring number here. And then I gotta multiply my delta H times 2. So I get negative 125.8 here. So negative 125.8. Okay, I think that's everything. So, because if I add these two, all three of these reactions together, I'm gonna get my 2C plus I'll get my 1O. So just to keep track, I'm gonna cross these out. 2CO and 2CO will cancel each other out. H2CO2, H2CO2 will gaseous form will cancel each other out. I'll get my water, 2H2O, plus my 2H2CO2 liquid. So after I add them all up, it looks exactly what I have here. All I have to do now is just add up all three of these delta H's, and it'll be my new delta H. So using my calculator, I got negative 279.4, and it's going to be kilojoules. So a little more challenging question, but all the rules apply. Okay, here's an example. Go ahead and try this on your own. The reaction we have here on top is what we're looking for, the delta H, and you got two steps here that you can manipulate to get to the final product. So figure out what your delta H is. Go ahead and click pause and try it out. Alright, so for the problem, I hope you got this. For the first one, you had to flip it because it wasn't in the right orientation. And you also had to multiply it times the coefficient times 2. So that changed all this, and this is how I got this number. For the second example, I also had to flip it, and I had to multiply it times 3 to get what I needed. So that's how the coefficients here came out, and I multiply that number times 3. Okay, so once I flipped it and I changed my signs for each, so remember you had to multiply and change the signs, you add up both steps and you get exactly what we're looking for, and we find out that our delta H actually equals a positive 1268 kilojoules. Alright, so I hope this helps you out.